Welcome to my talk, Turning Emissions Data into Climate Actions with CityCatalyst. My name is Mirco Rudolph. I'm the lead AI engineer at OpenEarth Foundation. And I'm excited to be here today. And I want to start with a number, which is 70%. And 70% is the number that cities are accountable for greenhouse gas emissions globally. And this is a very big number. And at the same time, cities lack a lot of information about the emissions that they emit. And they struggle to translate these insights into the emissions they have into actual climate actions. And the reasons for this are manifold. They could be lack of time. It takes a lot of time to actually work in this domain, lack of data, or just lack of knowledge. And at OpenEarth Foundation, we developed CityCatalyst, which is a tool that helps cities. It's an open source tool that helps cities do exactly that, create greenhouse gas inventories, which is basically an account of emissions for different sectors, transportation sectors, industry sectors, waste sectors, so that the city know which emissions they have in their city. And
best way is to
okay. I don't know who's talking there. So, yes? It's not just carbon, it's carbon equivalents. So methane, like three major, but carbon equivalents basically, so, yeah. And so also we help cities translate then these emissions into climate actions, and I will talk a little bit about what the climate actions are in a little bit. And yeah, so today I will walk you through how we use AI and open source technology to help cities understand their emissions and to act on those emissions. So here's what we're going to do. First, I will briefly, because I assume most of you are not too familiar with this space of climate, we'll talk briefly about why it's a problem if cities don't have inventories in place. And then I will talk about how we selected the model and also how we created our training data set. Then how we trained our model, and I will talk about a real-world application in Brazil where we actually implement all of this that I'm talking about right now, and about our challenges and how we try to overcome these challenges. So with this, let's start with why missing greenhouse gas inventories for your cities are a problem. I already said that cities are responsible for 70% of their global emissions, but only 5% of cities have actually an inventory in place. This is a super low number, and we can see that if we look at nations, nowadays I think every nation is kind of required to have inventories in place, but if we look at regions and cities, these numbers are drastically lower, and like I said, only 5% have actually emissions in place, which is super low. And this is also a big problem, because first of all, if a city doesn't know what emissions they are emitting in which sectors, they cannot really do anything against that. And the second reason is, even if a city wants to implement some sort of action, they are required, or like a prerequisite of implementing any action is usually by funders to get money for this, is to have an emission inventory in place. So basically the bottom line is cities are the top emitters, but they don't really know what's going on in their city and don't really know how to tackle this. Let's assume you are, or we are, one of these 5% of cities that actually have an inventory in place. This is great. It's a good job for that. But we still need to decide what climate actions we actually want to do. So how do we select the right climate action based on the emissions that we have? And this is what I'm going to talk about now. And first, I throw this word around a lot. So what is a climate action? Briefly, a climate action is basically everything a city can do to either reduce emissions, that would be a mitigation action, or to reduce climate risks, that would be an adaptation action. So for example, if a city decides to electrify the bus fleet, that would be a mitigation action because it would reduce emissions in the transportation sector. Different actions, obviously, you can have different actions to reduce emissions in the transportation sector, and then it comes down to actually what is this action in specific. So actions have different features, right? So actions can have different greenhouse gas emission potentials, like electrifying the bus fleet has a different potential than, for example, blocking all cities from noon to 3 p.m. or whatever. So there are different potentials to these. They have different implementation times, different implementation costs. They have co-benefits, like to stay with the bus example, this would probably also reduce or increase the air quality, but there might also be negative examples for an action. So if my action kind of relates to housing standards, it might increase the prices of houses. So there might also be negative co-benefits or like adversary effects for an action. And at the same time, there are city features. I already talked about the first one, the emissions per sector. So this is basically the inventory that I talked about. So it's super important that cities have this in place. There are climate risks, there are national strategies, which is important that the city kind of follows what is on the national level decided. And there are like lots of other features that define a city as a whole. So the idea is to match the action features with the city features and to then somehow decide which is the best feature or the best action for the city to take. So the question is, what makes one action better than the other action? So if I have two actions that reduce emissions in the transportation sector, obviously, not sure who's speaking here. So if I have two actions who reduce emissions in the transportation sector, obviously one action that reduces more emissions would be better than an action that reduces less emissions. But what if the action that reduces less emissions might be faster to implement and costs less money? So at what point would the second action be preferred over the first action? And this is a not trivial question at all. And when we started with this project, we had actually no idea about it. So we had to come up with a way to create a training data set and to kind of find out how we actually would rank these actions. So we created this tool. Nowadays you would say we vibe coded this tool. It's a climate action labeler tool, how we called it. And also we kind of call it like the Tinder or Bumble for climate action, because it does exactly that. It matches a city with a climate action. So on the left side, we can see that it's basically, it shows all the city context. It shows the emissions of the city. It shows all the information that we have, the climate risks. It's cut off in the bottom, so just a screenshot. And then on the right side, there are two actions. And the user can then select either I prefer the left action or I prefer the right action. And then when you do this for a couple of times, or even after one time, you get this little JSON output here, basically, which says, okay, for this city with this ID and these two actions, that action A or action B is preferred. So this is basically a tool how, not us, because we're not the domain experts, but what we did is we created some workshops and with 5 organizations and 20 experts. So we asked them to use this tool to label climate actions. And so these were all climate experts from different fields that we worked with. And they went in this tool and they labeled a lot of actions for us because, as I said, there's very little data out there that can be used. So we had to create our own data set here. And these are the results. And it's kind of interesting. So in 83%, the experts were decisive on their actions, which means they could clearly say action A or action B is preferred, which is great. Good job for that. But also in 10% of the cases, the experts were unsure. They didn't know, is action A better or is action B better? And super interestingly, in 7% of the cases, they had conflicting preferences, which means for the same city action pair, one expert said, I prefer action A, and the other expert said, I prefer action B. So this is super interesting to see. And basically, this means that we don't really have ground truth data to train our model on. So it's kind of like this gray zone area where different preferences and different biases of experts lead to different outcomes. So it's super important to keep this in mind that even though we have this training set, it's not easy domain and it's not really ground truth data. So anyways, we have now this data set, and now let's talk about how we use this to train our AI model. But first, let's talk about how we came up with a model to choose, or which model we choose. So as I said, we have 1,400 pairwise comparisons, including the unsure and conflicting ones. So it is a super small data set. I mean, small is always relative, but it's kind of small on the small side, and it's super noisy. All our features are like the city features that I kind of showed briefly, and the action features, they are structured and tabular form. And we had a big constraint. The most important one is that it has to be explainable, means if we use this tool to prioritize actions for a city, this action will take this information and base future investments on this. So it should be super explainable how we came to this decision. So it shouldn't be a black box. It should be fast to train. Of course, low compute is always nice, but the most important one was actually the explainability one. And at this point, we tried out a lot of different models. So we started with a heuristic model, so purely rule-based. We tried out machine learning models, like classical machine learning algorithms. We tried, of course, large language models, because everyone nowadays has to try out large language models. So we did all of that, but we found out in the end that the best performance we actually received with classical machine learning models, and in this case, a decision tree model or an ensemble model, XGBoost, because they are really, really good on small data sets, on small samples, and they're very strong for tabular data, and they even outperform on tabular data like most LLMs. So they're still very old, but still very powerful. So we had the best results with XGBoost here. Also, super important that they are very explainable. So with CHAP, for everyone who doesn't know what CHAP is, I will have a slide in a little bit to explain what that is. But so they are kind of much more explainable and quick to train. So when we started this project, there were, well, a lot of uncertainties. A lot of our data changed from week to week. We had to kind of see what we work with, our features, which features we had to use. So we had to be pretty quickly here on training, and we didn't want to retrain big models all the time. So this was also super important and super interesting. And also they have monotonic constraints, which is not unique to XGBoost, but a monotonic constraint basically is a way to tell a model, and because we are comparing two actions, so it tells the model if, for example, action A has higher costs than action B, action A is strictly worse than action B, which if you compare two actions, it makes sense. So this is the model that we choose. And here's some information about training the model. So when we started, we had like 60 plus features that were, some important ones, some not so important ones, mostly all the features from the city and the actions. They had also mixed scales, categoricals not encoded. So this is kind of like a typical machine learning pipeline. Whoever, of you guys worked in classical machine learning, this is nothing fancy here, so you will not be surprised of what you're gonna see. After these feature engineering, we basically boiled it down to 5 features that had the most predictive value. And this was super important because we have a small data set, like 1,400 training samples. So with 60 features, it's way too much. So we had to reduce the dimensionality here. Numerical values standardized, categorical values encoded. And also one thing that we did, we mirrored the data set for the sole reason that we have, if we make a pairwise comparison, we don't want the model to learn that, for example, just because one action comes first in the comparison, it somehow has an influence on the output. So we basically mirrored the data set that if we have city 1, action A, action B, it would be class 1, that we also have city 1, action B, and action A would be class 0. So this is just for enforcing anti-symmetry in the model and reducing auto bias. And the added benefit is that we kind of doubled our data set, but, good to have. And so then we trained the model. I basically just want to point out mostly the accuracy, because the rest is very standard. So 70% is not a great accuracy, but if we keep in mind that the data set is super noisy, it's also kind of not an unexpected result. Remember, we have 10% of untrue data, 7% of even conflicting data. So it's kind of noisy. And yeah, we're currently still working on improving this, but these are the initial results here, the 70%. But I will also talk in the outlook a little bit about this. Since our data set is balanced data set, we just, accuracy is the most descriptive value here. F1 score and all of these things wouldn't really add here, so we just kind of go with this one. So this is about the explainability using SHAP. So as I said, for everyone who doesn't know it, it's super important to tell cities and also to confirm with us that the model is working correctly. Here you can basically see just what it is. It basically tells us for each feature that we have how this feature influences the total decision of the model. So we can see that the action A has a higher reduction potential, so this favors to the right. It has more co-benefits, favors also to the right, but it's basically slower to implement and has higher costs, so it goes to the left. And it's equal on the risk score, which is basically the climate risk score. So you can do this for every comparison, and you can see what it's doing. Does it make sense? And also, if a city asks, or if a city wants to see how we came to the conclusion, they can say, well, actually, in this case, I prefer to put more favor on the co-benefits because for whatever reason this might be more important to them. Then with this, they have the possibility to do so. And so explainability is also, as I said earlier, a super important factor why we choose this approach. Now let's talk briefly about the real-world application, because it's super interesting where we implemented this and also how we started this. So actually the entire project started out of this Brazil CHAMP initiative, which is basically leading up to the COP. So this year the COP will be in Brazil, the UN climate conference. And so this is kind of like leading up to this conference. And CHAMP stands for Coalition for High Ambition Multi-Level Partnerships. And it's basically a program, from the Green Resilient City program, I have to read this, I can't remember this, from the Bloomberg Philanthropies Joint Program. And basically it's a project from Global City Networks, C40, and the Global Covenant of Mayors. Okay, lots of names in there. But basically what it is, it's a project with 50 cities and like around 225 million people. So it's a big project that influences a lot of people, which is super cool and super exciting. And the idea of this project is to advance the climate action selection in Brazil for the COP that is coming up in November, I think, to give cities in the broad the possibility to select climate actions based on their emission profiles and on their context. So this is basically what the project is about, and this is where we started to work with. We're also working with local consultants that know, the local cities, IK and Risa, just to name them. But yeah, super interesting project. Next, you're gonna get a quick overview. I'm not gonna do a live demo here, but this is just basically, I will scroll down in a bit. So you will see basically this is a front end that we built for the cities to use. So you can select different cities, and then you get all the context from the cities. You can see, sorry for that. You can see the climate risks, the emissions, all the city context data, and then you can see the top selected actions. I'll scroll a bit fast. And basically these are 20 actions that we ranked. So we created a database, which I will also say, I think on the next slide or something to that. So we created basically an action database that we also open source, so everyone who's interested, please have a look. It's an action database of like 300 actions, so like with climate actions, comprised from different sources. And we basically rank per city the top 20 actions. The top 20 actions, it's kind of an arbitrary number. It could be 5, it could be more. But basically because there's so much noise around it, we didn't want to say, okay, this is like the top number 1 action. So we kind of give like a couple of actions for the city, but they are all basically the top 20 actions the city can use. And we use basically a tournament ranking. So we have this pairwise comparator, and we use a tournament ranking that basically ranks all these actions against each other, and then basically creates a hierarchy of the top 20 actions. Yeah, so this is just the front end, what it looks like. And with this, I'm gonna talk briefly about challenges, because challenges, there were a lot of challenges in this project. The number 1 challenge that we basically started with is that there was not really a lot of data to work with. I mean, climate is super important, but somehow not many people work in this, so there's just not a lot of data available. So it's always kind of difficult to get data to work with. So when we created the climate action database, we had to work with different sources, and of course we have to homogenize these sources. They had like, different sources, meaning different fields, different descriptions, different values added to them. So this was some issues we had to work with brain trust and data processing. Also super difficult when we work with climate actions. Effects take time. If you have an action that you implement nowadays, it might take half a year or a year until you see effects, until you can actually measure it. And at the same time, this effect could be overlapping with seasonal effects or with economical effects, so you don't always really know, is this effect now purely because of a climate action or where does it come from? So it's just in generally a very noisy environment that we're in. Implementations are often city specific, so if I have one action that I implement in 2 different cities, the outcome will hopefully be similar, but it will not always be super identical. I also already said that we don't have ground truth labels. I mentioned that in the previous slides, and this is mostly in the dataset we're using because of the experts' biases and preferences. So depending on their background, they might rank or value actions differently. And the last one here is that we have variable data quality, which kind of goes back to the first one. We have different data sources, so means we have also different experts ranking different actions, and so depending on the experts and the biases, so we have actions in the data set that are very similar but still have very different, like very vastly different, for example, reduction potentials, which shouldn't be the case. So if the actions are very similar, there should be like a little bit variety, but we have some actions, or had some actions, that had like completely different approximations of the reduction potential. So we can see different sources, different experts. It all adds to a lot of noise, which is very hard to work with. So how do we try to overcome this? Luckily, when we started, we didn't really have any data except for some data we found on the internet and we could use from somewhere. But now I told you we have 50 cities that we work with, and actually we are currently expanding this to more than 5,000 cities in Brazil. So in the future, and currently right now, we will have a lot of data to work with. So the number one thing here is learn from the pilots that we have, and this will give us a lot more data to retrain our models and to be much more, to get much better results. So the number one thing we're going to do is gather data from these cities. So they use our tool, we see what actions they are using, we see how they interact with it, we see what they're implementing. So there's a lot of data we can get this. Also, we are in talks with them, we have workshops with them, so we see what's important with them, what works and what doesn't work. The second thing is that we are monitoring the implementation. So we know their inventories because I use our platform to create the inventories. And then we see which actions they are implementing, so we can also over time implement and monitor how this has an effect on the inventories, which is additional data we can use. Based on this, we have to improve our data quality. So I already said we have a lot of heterogeneous data sets currently, so we just have to make sure to align them more to make them more homogeneous. We will currently we have these 5 features, but we can already see that talking with cities, there are many more features that are important to the cities. For example, currently we kind of implement the national strategies in a way that how an action relates to the national strategy, but we're not actively using it in prioritizing these actions. So for example, this is just one example where we would update our data model to include national strategies and other features to then inform our model to make better decisions on the additional context that we have. And lastly, when a couple of slides ago, when I said how we choose a model, I said we experimented a lot with machine learning models versus LLMs, or even rule-based models, and that we only used a machine learning model because our data was tabular data. Now, talking with the cities, we see there's so much more data. Well, we kind of knew that before already, we just kind of to ignore it in the pilot phase, but there's so much more data which is not in tabular form, which is unstructured data, for example, national strategies, that we are now probably have to pivot to a more hybrid approach, using LLMs for unstructured data, combining it with machine learning models for the tabular data. So this is something we're going to experiment with, how we're going to do this. So these are just some ideas of how we learn from the pilots that we have currently, the pilot phase, and then improve the system. And yeah, with this I come to my last slide and to my final words, basically. So, I mean, there are lots of challenges, as you can see, and the biggest challenge is really the data. But at the same time, we can already see with the pilots and the implementations that we have that the system is actually still already quite successful. The cities, the actions that we rank for the cities, they fit often pretty well. Maybe not the top 3 actions in the top 20 that we show are the actually top 3 actions that they are using, but always in 100% of times they are like in the top 10 or something that they actually implement from the top 20 that we choose, which is from 300 actions, like a pretty good result. So yeah, this is our project, and if you happen to work in the climate space and have data that we can use or want to cooperate in any way, please reach out to us. That would be perfect. And otherwise, thank you very much. And other questions? Yes, please.
Did you try using IAM model and agent-based model instead of using the AI for solving it, or is it overkill?
I'm not sure if I understand the question correctly. Are we trying if we're using agents generally, or agent-based models? I mean, currently, no. So we only use the XGBoost because our data was, tabular data. We are looking into using more a hybrid approach, but currently we're not using that. Thank you. Yes.
Yeah, in terms of the data, have you tried maybe using information extraction with the LLMs to actually get more data?
Yeah, this is thank you for bringing that up. This is actually something that we are looking into right now, that we kind of want to, scrape scientific papers or just general sources to see where cities implemented climate actions and then get this data from there. This is actually something we're looking into right now, yeah. I haven't done it yet, but it's a perfect idea and we're going to do that. Thank you. Yes?
As of now, the results are just based on what the expert told you to create the dataset, or do you in any way forecast what the result will be? So like, as of now, in this city, there is this pollution, but still, if we implement the top 3 solutions, we will have 10% less. Is this based just on what the expert told you, or on any forecasting model or data that you have?
Currently, we're not doing forecasting. Currently, it's currently this prioritization suggestion based, so that for your city context and your emissions, these are the top actions that you should implement. We're not currently doing any forecasting that says if you implement these couple of actions, this will reduce by so and so. This is not what we're doing as of now.